Good morning, everyone. Today, we all have gathered here to celebrate National Science Day event. First, I would like to invite the dignitaries on the dais. For this, I request Professor Purushottam to escort Honorable guest Dr. Shivannayam onto the stage. Now, I request Professor Badhusudan to escort esteemed guest Dr. Nagendra Ji onto the stage. Now, I request Dr. Aisha Anjum to escort Honorable Secretary Madam Srimati Usha Gangadhara onto the stage. Now, I request Professor Revati Madam to escort beloved Principal Madam Professor Pushpalata onto the stage.
Hello, just.
I request Professor Purushottam to escort our Honorable HOD of BSc Department, Professor Hari Krishna, onto the stage. Respected dignitaries on the dais, my dear students and colleagues, a happy morning to you all. I, Salma Sultana, Professor of Department of Mathematics, extremely honored to speak the celebration of National Science Day. Wishing you all a very happy National Science Day. This event is celebrated to show dignity and respect to the discovery of Raman effect by the great Indian physicist Sir C.V. Raman, for which he was awarded the Nobel Prize in Physics. We'll always remember him for his significant contribution in the field of science. As Sir C.V. Raman once said, science is the gateway to walk. Through that gateway, let's walk together. This day has become still more memorable as it is the birthday of another great scientist, none other than Albert Einstein. Let's begin an event with a prayer to connect with Almighty and seek blessings. For this, I'd like to call upon Kavya, student of second year BSc, to present an invocation song.
ಗಜವದನ ಬೇಡುವೆ ಗೌರಿ ತನಯ ತ್ರಿಜಗವಂದಿತನೇ ಸುಜನರ ಪೊರೆವನೇ ಗಜವದನ ಬೇಡುವೆ ಗೌರಿ ತನಯ ತ್ರಿಜಗವಂದಿತನೇ ಸುಜನರ ಪೊರೆವನೇ ಗಜವದನ ಬೇಡುವೆ ಪಾಶಾಂಕುಶಧರ ಪರಮ ಪವಿತ್ರ ಮೂಷಿಕ ವಾಹನ ಮುನಿಜನ ಪ್ರೇಮ ಗಜವದನ ಬೇಡುವೆ ಮೋದದಿ ನಿನ್ನಯ ಪಾದವ ತೋರು ಸಾಧು ವಂದಿತನೆ ಆದರದಿಂದಲೇ ಸರಸಿ ಜನಾಭ ಶ್ರೀ ಪುರಂದರ ವಿಠಲ ನಿರುತನೆ ನೆಯುವಂತೆ ವರದಯ ಮಾಡೋ ಗಜವದನ ಬೇಡುವೆ ಗೌರಿ ತನಯ ತ್ರಿಜಗವಂದಿತನೇ ಸುಜನರ ಪುರೇವನೇ ಗಜವದನ ಬೇಡುವೆ.
Thank you, Kavya, for melodious song. I would like to call upon Professor Madhusudan to welcome the dignitaries on the dais.
Om Shri Gurubhyo Namaha. It is my privilege to welcome all these dignitaries and visitors to this event, National Science Day 2025, here at SDC Degree College, Kolar. Now, I would like to extend my warm welcome to our Chief Patron, Srimati Usha Gangadhar Madam, Secretary, SDC Group of Institution. Now I would like to extend my warm welcome to our patron, Professor Pushpalata Madam, Principal, SDC Degree College, Kolar. Now it is my honor to welcome our two chief guests of this event. Firstly, Dr. Nagendra Ji sir. I welcome you, sir. And also it is my honor to welcome Dr. Shivanna sir. I welcome you, sir. And also I extend my warm welcome to our beloved HOD sir, Professor Harkrishna sir. I welcome you, sir. And I welcome all my fellow colleagues to this event. I welcome you all, my dear fellow colleagues. And I welcome our college PRO sir, Arun Prasad sir. I welcome you, sir. And last but not the least, SDC superstars. My dear students, I welcome you all for this event. Thank you, madam, for this opportunity. Thank you all. Thank you.
Thank you, sir. I welcome you on behalf of everyone and heartily welcome to our event. Now, let's begin the event by the lighting of lamp. I request all the dignitaries to lighten the lamp. I request everyone to rise. all the dignitaries for making the event brighter by lighting the lamp. Light symbolizes knowledge, and by lighting, we can get rid of ignorance. Now, I'd like to welcome Professor Hari Krishna sir to introduce the honorable guest to us.
Thank you, madam. First of all, I would like to thank our chief patron, our president, ma'am, Srimati Usha Gangadhara, as well our beloved principal, Professor Pushpalata K, for giving permission to organize this event. Firstly, just I want to say the speciality of the day. Just Professor Salma told, we are celebrating this day as National Science Day. Actually, a delayed celebration it is. The National Science Day is actually on Feb 28. So because of some unavoidable constraint, we couldn't able to celebrate on the same day. And unknowingly and luckily, we got this day to celebrate the National Science Day, which is the birthday of a very eminent scientist, as Professor Salma told. It is none other than the person of the greatest science era, Professor Albert Einstein. And being a science person, everyone know what is the contribution given by Albert Einstein to the field of science. So being a science person is really a lucky. Being a science person is a boon, ದೇವರಿಂದ ಪಡ್ಕೊಂಡಂಥ ವರ ಅಂತಲೇ ಹೇಳ್ಬೋದು. Because other than a science person, the contribution to the society ಬೇರೆಯವ್ರ ಕಡೆಯಿಂದ ಕಂಪೇರ್ ಮಾಡಿಕೊಂಡ್ರೆ ಸೈನ್ಸ್ ಪರ್ಸನ್ಸ್ ನಾವು ಕೊಡೋವಂಥ ಕಾಂಟ್ರಿಬ್ಯೂಷನ್ಸ್ ಏನಿದೆ ಸೊಸೈಟಿಗೆ, ದಟ್ಸ್ ಎನಾರ್ಮಸ್. ಆ್ಯಂಡ್ ಆ ಕಾಂಟ್ರಿಬ್ಯೂಷನ್ಸ್ ಅನ್ನೋದು ಪ್ರತಿ ವರ್ಷ ಪ್ರತಿ ದಿನ ಅಪ್ಡೇಟ್ ಆಗ್ತಾನೆ ಇರುತ್ತೆ. ಆ್ಯಂಡ್ ಇನ್ ರೀಸೆಂಟ್ ಟ್ರೆಂಡ್ಸ್ there are two things that are emphasizing like anything in the field of science. One is a technique, what you call it as spectroscopy, and the field which cannot be explained in words, that is nanoscience. So being a science person, we should well aware with the nanoscience as well as spectroscopic techniques in order to convey the research trends, the techniques and the applications, everything related to nanoscience and spectroscopic techniques. We have esteemed persons with us, that is Professor Dr. Shivanna sir and Dr. Nagendra sir. Both of them will tell you about the complete details of nanoscience and spectroscopic techniques. And I thank Dr. Shivanna sir and Nagendra sir for accepting my request to come here and to deliver a talk. And after the talk, I had already requested our eminent persons to give an one-to-one interaction to the students that will be benefiting our students. Regarding other things, my colleagues will continue. I thank all my faculties, students, and management and principal and the esteemed guest for providing this opportunity. Thank you.
Thank you, sir, for giving a brief introduction about today's. And now I'd like to welcome Professor Sushma for the presentation.
Good morning, everyone, and a very warm welcome to everyone once again. It is my privilege to introduce our honorable chief guests, Dr. Shivanna M. and Dr. Nagendra G. Dr. Shivanna M. is a leading researcher in the field of chemistry with an impressive 16 years of teaching experience. He completed his post-graduation at Bengaluru University in 2010 and was awarded a PhD from a same institution in 2016 for his groundbreaking research in solid state and structural analysis and electrochemistry, focusing on water splitting and supercapacitance. Dr. Shivanna is a respected scientific journal reviewer for prestigious journals such as ACS, RSC, and elsewhere. His dedication to research has earned him the National Postdoctoral Fellowship from DST India and Kotari Fellowship. With around 49 publications, most of which are Q1 and Q2 rated, and several patents graded by DST and KSTA agencies, Dr. Shivana's contributions to the field are truly commendable. Currently, he serves as Associate Professor and Research Guide at Reva University, Yelahanka, Bengaluru. Dr. Nagendra Ji is a leading researcher in organic chemistry with 15 years of teaching experience. He graduated from Bengaluru University in 2004 and completed his post-graduation in organic chemistry in 2010. He was awarded a PhD in 2011 for his research on the chemical synthesis of peptidomimetics, focusing on endothiopeptides, peptide heterocycles, selenoridopeptides, and urea-linked glycosylated amino acids from Bengaluru University. Dr. Nagendra has an extensive research background, having worked as a research associate at CSIR ISCT Hyderabad and as a postdoctoral scientist at Technical University of Dortmund, Germany. His work on the synthesis of therapeutic analogs for tobacco cessation and drug targets on EGFR and AKT is highly regarded. With around 35 publications and several patents to his name, Dr. Nagendra has also actively participated in numerous national conferences. He currently works in Reva University as Associate Professor. Thank you. Thank you for this wonderful opportunity.
We are really inspired by your achievements, sir. Thank you, madam, for the informative presentation. Now, I am glad to invite Dr. Shivanna M. sir to enlighten our students about nanomaterials. Yes, ma'am. Sir will talk about the nanomaterials, ma'am, about the topic.
Are you hand over the session?
Yes, sir. Ma'am, for a few minutes he may talk, ma'am. After that, talk.
They have already given instructions, no, that only few minutes they have to put up.
Sir told, ma'am, within 1.5 hour.
No, no.
I hope all of you had your breakfast and almost it's going to be lunchtime in another 1 hour. So at least whatever I'm going to talk about this nanomaterial, let me just give you whatever we see in nature, whatever we could see is macromolecule, which are bigger, which we can easily see. Correct? But the important properties are not from like whatever we can see. That the property is mainly depends on the size. So we look at those properties are those materials which are very good and which enhance most of the properties just by increasing size. So this field is mostly depends on the size of the material and which enhances the different properties. Okay. Whatever I'm going to talk is completely about basics. I'm not going to talk too much technological oriented because it's too much vast field. So let us try to look at the basics, the introduction part of it, and mostly some of, I don't know whether in the degree or some of the students might have already looked into this basic topics, but still we'll look at those basics. At the end, I'll just touch upon some research what we are doing it. So I'm not going to talk about too much deep about this research here. Let's go further. So what do you mean by a material like nano means? So when the one what we can see out with our naked eyes, what is the minimum size that we can see with our naked? What is the minimum size that you can see with our naked eye? Millimeter. At least you have two lines which are separated at least 1 millimeter. If you want to see even more smaller than that, micrometer can naked eye. How to do? If you want to see the micrometer size particles, or molecules or biomolecules, whichever, use microscope. So you want to increase the resolution power with our naked very less resolution power. Then you have to increase the resolution power by using the light microscope. So that is only for micrometer size. If you want to look at even more smaller, so then which you can even not even differentiate with even with the light microscope also. So that's why we are looking at here this pointer works, sir. So when you say nanometer, say a material, any material which size is upon like 10 to the power of minus 9 meter. Like 1 nanometer is nothing but 10 to the power of minus 9 meters. So those materials which comes around 1 to 100 nanometer, those we call as nanomaterials. Okay. But if you look at this size, you can see some of them. This is what is this? Your blood RBC molecule. So what is the size of RBC molecules? It's about micron size. At least with now light microscope you can see. But further if you go on below this, very nanomaterials you cannot see it, but we have a different technology that we can talk about, like we have scanning electron microscopy and other tunneling electron microscopy. But this scale which goes to bottom. Like even if you look at this, some of the small molecular even if you look at ant is around nanometer, like millimeter. If you look go below that, even the fly ash, even the small molecules, even this virus or even coronavirus, they all come that you cannot see. So that property, how can you understand them? How can you understand or how can you study them? Is comes around that. So this is scale to the idea about the macromolecules to the micromolecules to the nanometer. So all these nanoparticles are molecules and are in nanometer size. So same here, like this is also it's like how big a nanoscale. So when you have 1 meter scale to the 1 mm, further down this will be micrometer, nano. So when you look at nanometer, you can see the cholesterol, the molecule. I don't know how many of you at least know the cholesterol molecule, the formula. So if you look at one molecule size, it comes around 1 nanometer. So like it's not like nanometer, nanotechnology is not. It's now people know now, but it is there already in the nature. Whatever I gave an example also, nanomolecules like the molecules or water molecule or any small molecules, they all exist. But we don't know, we were not knowing this structure actually and their sizes even more until the science is developed. But this is one of the people already almost talked about who studies nanomaterial. This is a Laker gas cup which were there in the UK. But this, if you look at this cup, the property is different. If you put a light and shine in one direction, you'll get a different color. But if you pass towards like on the inside, when you do the light through the transmission, you'll get a different color. So when it transmits, it becomes almost reddish, pinkish color, red pink color. But when you look at reflected, when you shine from the opposite direction and if you look at only reflected light, the color is different. People are not knowing, like the same cup only. You are not changing anything. But just looking at light direction, whether you shine from the back side, when you are looking at transmission side or reflection side, this color changes. What is this? What makes this color change? So people, it was like it's around 1990, but still people were not knowing. But to understand that, they looked at this is the reason is because of that cup has more nanoparticles around in the nanometer size. So those are the reasons to have this color change. And further, all of you have seen lotus leaves. Well, most of the places when water falls, most of them absorb or at least stay on the leaves or other places. But when you look at the lotus leaves, the water molecules or water droplets will not stay on them. They will die slightly. Okay, they move. I hope this is fine. But when water molecules pass on these leaves, they won't stay. They just roll off. But when you look at just with naked eye, you cannot say anything. It's just a leaf. But when you look at in the microscopic level with SEM or TEM, look at the shape, like what is the morphology? The morphology is a different array itself. So this morphology which makes this water molecule, the molecular size, the water droplet size and this shape which doesn't make water molecules to stick on, like it becomes a hydrophobic in nature. I hope you know the hydrophobic and hydrophilic. So which water loving or water hating, what we can see. So this property, this surface property is the reason. That's why the molecules, water molecules are any droplets which will not stick onto it, but it will move on. So that is because once again, this is the size of this, each shape is around nanometer size. So that is the one of the reason. So one more thing you have seen, nature. Now when you are looking at the nature, now we have to learn from the nature. Whatever the science development, whatever we do, whichever the science or technology, we are trying to mimic or we are trying to copy from nature only. Nothing like whichever the scientist, every scientist is trying to understand nature, that's all. We are not going against nature or we are not doing anything very, very great which is not at all existing in nature. Okay, we are trying to understand. But if you look at this is your butterfly. You can see that butterflies which has different colors. The colors, if you look at eye-catching colors, very, very beautiful colors, and the flies. But why is that the color is so different? So even that color makes these nanoparticles, the shape of the nanoparticles or how they are shaped, that mainly causes the color change. You can see not only this one, if you look at some of the butterflies which have multiple colors. So all this is because of this, what is the shape and what type of nanomaterials which caused that. So it's once again application of nanomaterial. So this is a basic, what is happening, hydrophobic nature of the lotus leaves, which has that. If you look at these two figures, when you have any material in which the surface is smooth, okay, when it is smooth, if you look at this, it is highly smooth in nature, when your water droplet comes, it can take up on those molecules and it won't even carry them. But if you look at this surface, you made it a nanoparticle, like little bit bruise type, which are nano size, which are in the 1 to 100 nanometer size. When water molecule or any droplet comes around, that take up the dirts present. So this property is being used in the present scientific development. They are using like the fabrics which will not even absorb the dust. Okay, hydrophobic in nature. So they say if you have such fabrics, no, you don't need to wash, because it won't absorb water, it won't absorb any grease or any dirt. So that is property is being like that scientific development because of these nanomaterials. So one more thing, you have seen the lizard, correct, in our houses. But the lizard can go anywhere, it can even stand here, it can hold. Normally when you say like you cannot hold, now opposite, because when you are holding it there, the gravitational force is to this. They should fall down, but they are not falling down. So that is once again because of the nature or the property of the palm, whatever you have here. So we call this Gecko feet effect. So this feet has, if you look at further microscopically, so these are the shapes is nanometer size. That nanometer change, whatever it holds, it can hold in such a way that it sticks on it. It acts as a gum, but it won't be so strong. But it can even just move that, and it can keep moving. So if you look at microfibers, it will have. So these properties made that they can easily hold anywhere. They can catch. Even if you looked at the lizard's tongues or maybe a frog tongue, how they will catch the flies. And it just, even that tongue has the gum type. Even if you look at further, even those are also some of the nanomaterials which acts things. But to understand, the first person to look at this scientifically or to understand these things, now this is already there. Whatever I spoke about till now, it's almost all our nature. Whatever it was there in the nature, that we are trying to understand. But who is the person who started looking at this, even though it is already present in the nature, but people were not worried, people were not interested in looking at those. But the first person who spoke about this is Richard Feynman. He is a physicist. Okay, he is not biologist or a chemist or he is a physicist. But he was doing some more experiments as a scientist. Now, we always scientists should not like the physicists look at only physical properties, or chemists look at only chemical reactions, or biologists look at only biological actions. It's not like that. In scientists, they have to think each and every part. Like when you're looking at something, what is happening? You can have like each, when you're looking at, when you're dialing money from morning to evening, you come across so many things. Just think in science, and in the science mind, you can try to understand the microscopic changes. Then people you get an interest also. But this person was, even though he's a physicist, but he was trying to understand the materials, properties, and first he was given a word like this sentence. He said that there is plenty of room at the bottom. So what is it? So bottom is like wherever it is, a small size. Even a small size, plenty of things are there, which we cannot see with our naked eye, but further he could understand, we can explore a lot. So that's what is meaning. Then he said a new field in physics, which is nano, or nanophysics, or nanoscience. And he's the first person, and that's why we call him as Freeman. But he did not tell nano material or nanotechnology or nanoscience, but he said only there's something which you can understand very, very small size. But the main term is given by this person, Terubushi. And he's in 1974, but even though he's given 1959, look at the time, how much time, almost 15 years. 15 years it took the new coin, the world to coin. And he said the nano, the name, in Greek, they say nano means a dwarf, a small size. Okay, that is the one, and he is the one who gave the name. Maybe he is the person who has invented the baby is born, it's born long back, but he found out this is some baby with a nanomaterial, but the nomenclature has been given by this person. Further. So, okay. Then, if you look at the timeline, so you can see almost 2,000 years back, there exist air dye. Now only we are looking at the air dye, but it exists long back. We were looking at the sulfide nanocrystals, but that time people don't know whether it's a nanomaterial or whatever. They used to look at some material which they used to use it for dyeing their hairs. It was so old. After that, 1,000 years back, after this 2000, like not 1,000 years back. So gold nanoparticles was prepared, but they were not knowing it. But they prepared a material with a different size, they saw a different color. But that understanding is being recent only. Then only Richard Feynman has come to say this is something which you can understand a lot in a small size. Then the nomenclature, nanotechnology has come. From this, if you look at, then the technology has moved a lot. The first, molecular electronic devices, where electronics people have started using it, a technology, where they can make, they wanted to make smaller size devices. If you look at some 20 years or 30 years back, what was the size of a computer? Size of a computer was as big as a room. Now you have a small, even smaller than your palm. So then this technology is important, is like electronic devices or electronic parts. Something like transistors, so which made it smaller size. So that's why electronic devices like this IBM is the first company which invested money to understand or to develop this nanotechnology. And they use this nanoprobe microscope to understand nanoscale, like microscope which you can understand the structure. Then there is one more development like buckyballs. What is the chemical formula, at least general chemical formula of buckyballs? Carbon materials. Huh? Any idea about some different carbon materials? C60, C80, never heard about. So that carbon material they started like a zero state. I'll talk about the classification. So you have a 0 dimension, 1 dimension, 2 dimension type. They have this 1980 to 85, they started looking at the keyboards like the carbon materials. Then once again the IBM is the most one, which is the first starting, the company which started this research, and they are going further. And then once again the nanocarbons are carbon nanotubes. Now different morphology of different allotropes of carbon is there, which can have different properties. So one is buckyballs, you have carbon nanotubes. Further, there are a lot of research is going on now. So to understand that, so these are some instruments. You need, this is called scanning electron microscopy. We have something tunneling, transmission electron microscopy. STEM, there's a lot of instruments which you can understand sizes and technology. So then only people looked at how do you classify. We said the nanomaterial, we said like 1 to 100 nanometer size, we call them as nanomaterial. So they have classified them by looking at, once again, all three directions, all three dimensions. So one is zero dimension material, where all three directions, you look at X, Y, Z. If you look at that nano as a nature, normally we look at X, Y, Z direction, and what is the size, the length, width, breadth. Okay. So in such cases, when you have a material which measures, all the size X, Y, Z, all of them should be less than nanometer. In nanometer range, there are zero dimensions. You can see this carbon dots. The buckyballs are fullerenes. These comes under zero dimension, where all X direction or Y direction or Z direction, all three directions, the size is less than 100 nanometer. So they called as zero dimension material. The next one is one dimension, any one direction. In maybe X direction or Y direction, Z direction, that can be more than nanometer. Other two directions should be less than 100 nanometer. Those materials are called one dimension materials, but the examples are these nanotubes and nano rods. It means that only one direction their length. It can be meter size. Normally you won't get that meter size, micron size or millimeter size. Those are called as, if you look at here, 1D along only Y direction, or it can be X, any one direction. It can be more than nanometer. But two dimension, along any two direction, maybe X, Y, YZ or ZX. It can be sheet type. Only one direction less than nanometer range, or other two, it can be bigger. Three dimensions, all three directions are bigger. So all of bulk materials are called as three-dimensional material. This is a table where you can compare. All these are zero dimension. It can be coarse shell nanoparticles. So nanoparticles, if you say nanoparticles, they won't, when you are decreasing the size, there is surface area increases, they try to collide. Means they collide and they even combine to become bigger particles. To avoid the bigger particles, we make that some coarse shell. Outer side, make some capping and all. So this size is supposed to be less than around 100 nanometer. And these are any nanotubes or carbon nanotubes or any nanowires, all of them comes under one dimension. This any sheets type. So 2D and the bulk in the 3D. Some more examples of this. Zero clusters, nanotubes, films, polycrystals. So what does it make, like when you say like what is the importance of nanomaterial? We have already know all this bulk material. What makes that these nanomaterials are so important? We are talking about everywhere technology, nanotechnology. Either you can look at any field, there's a nanotechnology has come. So what it makes this material so special? That special is because of the properties. Main properties are when you decrease the size, the surface area increases. When you have more surface area, there is more active sites as a chemistry or whether like a physical absorption for everything, you need a more surface area. First, surface area enhancement and something quantum confinement I'll talk about in the next class. How do you say that, sir, even if you take bigger size or smaller size, how does surface area increases? To have a field, you look at this calculation we have just looked at. Any cube which has like 1 meter. What is the surface area of a cube? What is the formula for surface area of a cube? The square. What is the surface area of a square? Huh? Simple formula. any two sides, what is the side? I have given you already. 1 meter is one side. A is, if this is A, then what is the area of a square? Only one. I am talking about only one side. A square, correct. So it is one side, but in a cube, how many sides are there? 6 sides. So 6 into 1, 6 centimeter or meter, whatever it is, the length, so it becomes 6 meter square. Let us cut this cube into 4 parts. Not 4 parts, almost it becomes 8. You cut like this, Okay. Is it now is fine? Okay. So when you cut this cube into like here 2 halves, and like here 2 halves, and like here 2 halves. So totally it becomes 8 cubes. If you look at here, 1, 2, 3, 4, there's a back side also 4. Totally 8 cubes. Now what has become a side? What is a side? Now each side in a cube. Now here 0.5 meter. Correct. Now find out the area of each cube. What is the area of each cube? You have 0.5 each side. Okay. 0.5 into 0.5 is 0.25. 0.5 into 0.5. I am not asking addition. It's a multiplication, correct. 0.25 is one area, like the square of each cube. So you have 6 square. So it will be 6 into 0.25. So you'll get 1.5 meter square. Okay. So now 1.5 meter square in 1 cube. How many cubes are like that? 8. 8 into 1.25? Sir, 1.5. It will be 12 meter square. You will not have anything else. You just cut one cube into, you made it to 8 cubes. That volume remains the same. Volume has not changed. But surface area has increased as by now 6, here 12. Almost doubled. Once again, if you cut each cube, like you make it like a 3 house, totally it becomes 27. If you make the same 1 cube into 27 cubes, the area has become 18 meters square. Okay. So surface areas keep increasing. As you break down into smaller pieces, surface areas keeps increases. But volume remains the same. Correct. Volume will not change. Only surface area increases. If you look at this in the nanometer wise, in the nanoscale, if you take 10 nanometer and if you take it will be like from the maybe 100 nanometer to 10 nanometer, it has increased to 20. If you even decrease the size, it becomes 50%. Surface area keeps increases a lot. So this surface area property is very much important for many applications. Okay, this is one of the. So one more thing is quantum confinement effect. So you know that at least, but if you want to understand this, something you need to know about the solids. When you look at the solids, their electronic or energy levels. So something we have valence band, conduction band. I hope you guys know these words. In metals, both conduction band and valence band are overlapped in metals. In semiconductors, they have a gap. But in insulators, the gap is too big. But the valence band, conduction band, within that they are continuous, like overlapping bands. So these are the This is your valence band, this is your conduction band. So they are overlapped. When you have a bulk material, bigger size. But when you try to decrease the size, look at here, this gap between the different energy levels. But when you look at here, the gap is started. The energy levels has become a discrete, means there is a gap between different energy levels. You decrease the size, this energy gap also advances. Why it's so important, this energy gap? Whatever we see, at least I'll talk about macromolecules. See, we see the different materials, correct? And we see the different colors. What is the reason that you are seeing different color? Not only just reflection. So each material or each compound has some property, they'll absorb the light in. Mainly if you want to see the color, what range of electromagnetic radiation that it has to absorb or it has to emit? Visible region, correct. So only in visible region that we can see, or that we can, our eyes know, has only a property that it can only see the visible region, which differentiate the different color. So that is because of the property of the material which absorbs and emits. Now whatever we see color is because of the emission, not because of the absorption. You know that it absorbs different wavelength and it emits complementary wavelength. So that gives you the color. So that also depends on the energy gap. They absorb the energy, some light energy, then it goes to the excited state, and while coming back, it gives you the emission. So that is the one which makes you the color. You need this energy gap there. So this energy gaps is very, very, depending on what wavelength emits. Depending on that emission, we see the color. So to understand this, if you look at this, the same material, this is completely a gold material, but you have a different sizes, like 6 nanometer to the 2 nanometer. Same compound, only size difference, see the color. So completely optical property changed. Okay, so this is because of the material sizes only. So that is once again the energy gap changes. Okay, so that what we call as quantum confinement. Quantum is like as you decrease the sizes, the energy levels also changes. So which makes the optical property also change. And even that, not only this optical property, it also affects electrical property and magnetic properties. I'll also look at here. So these are once again the same. Same compounds with a different size, you have a different color. If increasing the size, wavelength also increases, the frequency decreases, the color also will change. So this is the density of states. Here the continuous, the bands are continuous. As you decrease the size, it starts breaking up, it becomes a line type. The energy gaps is decreased, completely discrete. So the sorry, yeah. If you look at this here, one is shape, another one is just we looked at the bulk gold. Normally bulk gold is glittery in color that we can see, but when you go to the decrease the size, completely changes, different color. Not only property, their conductivity property will change. Even some of them becomes even highly conducting, some of them become semiconductor. You can play with the size, you can play with the electronic property. And even magnetic property will change. You can make even superconductors by decreasing the size and changing the property. Also that mechanical property. Diamond is stronger as a bigger size. But even you can make carbon graphene. You would have heard about graphene. Graphene is a single layer of carbon. The graphite? Graphite is, you have a pencil lead. You can easily break that. If you just press little bit force, it will break. Correct. But if the same graphite, that's a multi-layer of graphene sheets. But if you try to take out a single layer of graphene, that's so strong, it's stronger than steel. It's said that it can even hold a helipad, a single layer of graphene. So mechanical strength is so high. It's because of single layer. If you have multiple layer bulk, it becomes brittle. So that much of property would change when you're looking at, when you decrease the size. So a lot of properties changes happens when you decrease the size. So this is about properties of different nanomaterials. Let us look at synthesis of, how do you synthesize them? There are different methods of synthesis. I'll touch upon only methods, not so much detail, so that becomes too much depth on it. So there are different methods, like you have a physical methods and chemical methods. There are instrumentation methods to make them as nanomaterials. Mainly we call them as, one is top-down method, the other one is bottom-up method. The top-down means you take a bigger molecule or bigger any material, you try to make it smaller size, break it. So that we use like mechanical ball milling, etching. So these are the methods we try to break it into smaller size. And this is different sputtering and lithography I'll talk about here. And chemical methods we have is bottom up. We take like metal salts. When you take metal salts like ions, when you take these metal salts and add some precipitating agent like base, so they form a nuclei, they start precipitating and become a bigger particles. So we call them as, that's a bottom-up approach. Smaller ions to molecule, okay, 2 nanomaterials. Okay, this is this top-down approach, bigger to smaller, decreasing the size. This is bottom approach, smaller ions to molecules. So these are the methods use top-down approach. One is sputtering, chemical etching, thermal ablation, laser ablation, mechanical milling, ball milling, explosion process. Here mainly you do is different energy. Sputtering you use different energy, chemical etching you will be using different energy to break down into smaller pieces. Mainly these two, mechanical and ball milling, they will be using mechanical. And here and laser energy and even heat, this is sputtering with radio frequency also. Here you can use explosion type, mostly we can use it even nuclear energy. Maybe we are not supposed to use because it's very hazardous. So this different methods. This is chemical methods. This is bottom approach. Chemical precipitation. We use method, hydrothermal method. Maybe these words are, I don't know whether it is completely new for you, but some faculty who are doing research, they may heard about those salt gel method, all those methods. See, when you're looking at mechanical, as I said, you can break it up. Here, I'm little bit look at the ball milling. The ball milling method, they'll have steel balls, which are strong steel balls, and you put bigger bulk material in that, and it's a closed vessel. And they'll keep rotating. When you keep rotating with the high speed, the balls, we have a different iron balls, they'll go and collide each other. They collide with the nanomaterials also, like bulk materials. They try to break it into smaller pieces. So that process is called ball milling. And one more is electrospinning. Now the polymers, when you have a polymers, either different polymers which you can make it as a gel type of polymers. From that polymers you can make a needle type, fibers type material. So that we use electrospinning. So what do you mean by electrospinning? You take a liquid sample, these polymers, and use electrical energy and you spin it. You have either, you can two things. Either you spin with this base, with this high speed, or you can even make this also as the tip. This is a place where you are pouring up your wherever maybe polymers or any composite material, and there is a needle type very small hole which you are pouring it up, And you can, the power you can make, use the power voltage to drop down and to spin. It spins with a high speed, and the hole of the tip of the needle is very, very small. With high speed, it's holding, it like is spinning it up, so there it forms as a needle type compound. So we call them as electrospinning. We are using electrical energies to spin to make a small size. We call them as electrospinning. You'll get all needle type or fiber type material with a nano size. And one more thing is, this is a lithography. Lithography mostly use it in to make this PCB. Now the printed circuit boards, whatever we see now is small chips, which will be there in your computers, laptop, or mostly the small devices. What we have is mobiles, even more smaller devices, electronic gadgets. This watch has the PCB, which is very, very small. How do you make that very small micron size, nano size PCBs? Using this lithography. First they take a base material, and that they normally coat it some conducting material, maybe a gold or copper. So maybe using the electro deposition method. After that, they'll make circuit. Circuit is everything is now digital technology. They'll use it. Drawing. They make a drawing and they print it on that. After that, wherever you want connectivity, apart from that other area, they will mask it. So they can see the masking, and that you can coat it. Wherever you don't have a mask, there only metal connectivity you can put, maybe oxides or some metals. Other masking area, you don't require any connectivity. Okay. Only those areas which are not masked, only the connections will be there. And there you can mask it, and then you once again electro deposition. These sizes are very, very nano, like very, very small. You can make all connectivity within maybe 1 centimeter, not 1 centimeter, like even 1 mm, 1 millimeter square area. Within that you can make a lot of circuit. If you look at old computers, the PCBs are look like maybe 10 centimeter square, bigger size, or even 20 centimeter square. Now the same thing you can make it within 1 micrometer size. So that you will be using such lithography method. And this is a sputtering. Sputtering where you take, if you look at in this figure, this is the actual instrument, how does it look? But if you look at here, this is what the mechanism, main work. Here you will be using some base material, and this entire thing you will be using mostly the argon, noble gases, argon or neon, and within that this is a gas, and you have, this is a base material which you want to coat it on the substrate, and you want to make a nanomaterial on the surface. You have base material, you give electrical energy here, and which makes, and which high voltage, which starts making the atoms. So they becomes atoms here, and which will collide with argon or neon gases also. With high energy, they will go and sit on this. Sputter means with high speed they will go and sit on the surface of a base material or substrate. You can, by maintaining what is the potential range what you give, can have a different shape. You have a different, that you can play with the potential what you give, and you can actually make different nanomaterials. So this method is called nano sputtering. People make nano tubes here, nano wires, different shapes using this. And laser ablation. Laser, you know that laser is, what is the difference between a normal light with a laser light? You have here in this white light, you have all the wavelengths. When you say take a laser, it has monochromatic light with high intensity. Wavelength is same, but intensity is very high. And it is narrow, it will not diverge, it will be completely converged. If you give high energy monochromatic light, if it hits on the material, it can break. It can break this bulk material into small atom size. Those atoms will go and sit on any substrate, if you keep it, it will go and sit on it, you can become a nanomaterial. So that property, using the laser energy, you can make nanomaterial. And there's other things as bottom approach. So how much time? Huh? Okay. I think decrease this, because these are the chemical methods. These are whatever I discussed, mostly physical methods. These are chemical methods are from bottom approach, ions to molecule. Okay. So if you're looking at that, first thing is you have ions, maybe a different cations and anions. You take a metal nitrate solution. If you take nickel nitrate or iron nitrate or even calcium nitrate, whichever the metal ions. So if you put it in water, they dissolve. It will be ionic in nature. But from that, if you want to become a bigger particles, you need to add some base. You some base, maybe NaOH or KOH or whichever base material, even sometimes ammonium hydroxide, ammonium chloride, the base material. Then these metals will react with OH, they becomes hydroxide, mostly hydroxides. When you do the base material, when you add bases, so they form nuclei. And these small nuclei, the nuclei are very, very small, smaller than nanometer. But they try to combine to become nanomaterial size, and the nuclei, and then they grow. So then the smaller nuclei, then it gets growths. You can control the growth also by using different other methods. So by using this growth metal, you can make different nanomaterials, even different shapes also, different morphology. So there are a lot of papers, people use it, different complexing agents also to have different morphology. So that is here. Wet chemical methods. This is salt gel method is one where you take metal nitrate solution, you add some reagent where it forms a gel. Initially it forms a gel, like jelly material. Then you heat it to high temperature, maybe 400, 500 degree calcination. So it becomes nanomaterial with high porous. So that is salt gel method. And self-assembled monolayers. Here, first you can take bulk materials, or you can have a single sheet material, and you can even assemble the different layered materials. This only works for the layered materials. Even emulsion, for oily type of materials, you can form an emulsion, and pyrolysis. These are small sprays into bigger molecules. And use gas condensation method. You can make take a solution and you pass high speed gas, inert gases, which makes that liquid into small sprays. Then they combine to become a nanoparticles. So if you look at here, you have these are the material. You take and you heat it with electrical energy and you evaporate, become a smaller molecules, and they'll go and coat on this substrate. They'll too high energy, and it will be like less energy, like it gets condenses to form a nanomaterials here. There is a lot of advantage. You can make different sizes, different shapes, different morphology with this inert gas condensation method. Is that thermal evaporation is you take material and heat it high temperature, they evaporate, and they'll go and condense on the substrate. Even there also, with using different solutions or different complexing agent, you can make different shapes. Even you can coat on different shapes. When only you can have a substrate with the surface modified, you can get different shapes also. And this is, once again, you can use either heat or potential energy, like potential current, to make nanomaterials here. And this sputtering also already we looked at. So application wise, just some slides are only application. It has application all over the field. Either you can see even medical field, in a biological field, even healthcare, even to understand, even they'll make even transport, some of the, if there is a heart blockage, they use nano robots now to even remove the blood clots. So they use a lot of nanomaterials. You don't need to cut now. just they'll pierce one needle type, they'll pass the nano robot, they'll go and remove the clotting, blood clotting, and it passes itself, removes that clotting. And in environmental, to precipitate or to remove the carbon dioxide or any other hazardous gases, or to remove the small particle size also, small particle nature, you can use the nanomaterials. And energy, mostly the batteries and energy field. You can have we have electrochemical methods, either batteries or fuel cells, where a lot of nanomaterials are being used. And here if you look at all these applications, mostly these layered materials, graphene, carbon nanotubes, fullerenes, amexins, 2D. It has biosensors, supercapacitors, all this carbon dioxide capture, fuel cells, all these applications, everywhere you have nanomaterials. And in biology field. And you can use this material to form a water repellent, fabrics, or even wherever you are using, where you don't want to stick on any dirt material, or it should not absorb. You can use water repellent material. And optical changes, you can use anti-static properties, like that anti-static property, like if you rub your hair itself, sometimes there is a accumulation on the hair. So there is static property. Some people even feel, even if they touch some instrument, they say, sir, I got shocked, but there was nothing. So it's all depends on their cloth or what they are using, like wearing it. So nylon material, they have most of the nylon material, they have static property. They absorb the charged particle. When you touch on something, it just discharges. There you feel electric shock type. So that is because of the anti-static property. You can make such material also, like static materials to anti-static material. And wrinkle resistance. If you have such material, you don't need to iron. There won't be any wrinkle. And even you can enhance the stretching material, change the color, and the antibacterial odor control. If you have such cloths, you don't need to have all this. It won't stick, either sweat or any other gases. It becomes completely antibacterial and anti-odor. And even sensors. That sensors, everywhere you have sensors. So all this, and even the agriculture, they will be using a lot of nanomaterials to enhance the even yield, or to avoid antifungal, even fertilizers. They make good fertilizers where it absorbed by the plants. All pesticides everywhere. Anyway, just 2 slides. I just show you. It's already time up, I guess. This is some of the research work what we want. I think some of the students have already looked at our labs. We work on electrochemical energy conversion. So where we try to split the water into hydrogen oxygen gases using different catalysts. So we prepare catalysts, different electrocatalysts, and we looked at their activity to decompose water into hydrogen, and this is hydrogen HER, this is OER. With the time constraint, I have just given you some papers what recently we have published in ACS journals. All these are recent journals only, we have published it. I just add any doubts of that, just get clarified now. Any questions? Because I did not go through the research also. Anyway, at least these basics you understood. Ask, even if it is a silly question also. Nothing is silly. You may feel this is silly, but at least it will help for somebody else. Nothing? It means that you understood everything, or nothing understood. Only 2 meaning there. If this first one is there, then I'm happy. Here. Okay. This, anyway, that I did not discuss about my research work only. So this some of my students who worked on in the labs and they got these papers. And those MSc students, we use our MSc students mostly because we have the project work, they do it, and with that they get papers also. They'll either go to for PhD, some of them are reaching out of country also. If they get PhD papers in MSc itself or BSc, you have opportunity in abroad also to get PhD also with the fellowship. You don't need to pay. They'll pay you for your PhD, and you can even earn money. And with that, I'll thank everybody, and I thank Hari Krishna sir and our management given us this opportunity to talk about. Yeah. Now, if you guys have any doubts, you can even ask me afterwards also. I will be available outside, not today at least. I'll give you my number also. You can even message me. Thank you.
Thank you, sir. That was a wonderful presentation. Since the nanomaterials is a completely new topic to the BSc students, so with your presentation, possibly the students will get some enthusiastic initiation to go through the nanoscience. Thank you very much, sir.
Thank you, sir. We learned many things that were new to us till date. Now, I would like to invite our esteemed guest, Dr. Nagendra Ji, sir, to deliver the talk about the spectroscopic techniques and career guidance for the students.
Yeah, very good afternoon. Hope it's a lunch time. I'm not going to take much time. Okay, I'll finish within 20 to 25 minutes. Okay. So first of all, I would like to thank the management of this campus, Usha Gangadhar Madam, Secretary, as well as your Principal Madam for giving us an opportunity to present our work over here. And I also thank your chemistry HOD Hari Krishna, being very enthusiastic and supportive for all of you students. And many of this batch already going on. Okay. In my presentation, I'll touch upon spectroscopic techniques. So, some of my work is reduced by Dr. Shivanna by his presentation. So, what he spoke is on the nanomaterials, correct? So, how to prepare the nanomaterials is good. Hello? Yeah. So, you got how to prepare the nanomaterials, right? And you can prepare the nanomaterials, but once you prepare the nanomaterials, you should know what is the structure. Okay. Once you prepare, you should know the structure. So there are different methods to identify the structure or know the structure. That method is called as spectroscopy. So why we need to know the structure? That is very important. So any chemical, any material, whether it is a nanomaterial or a drug, anything, if you want or synthesize, you should know its structure. Only if you know the structure, then only we have to proceed further. So what is the importance of the structure, you know? What is the importance of the structure of any material or drug? You have prepared some material in the laboratory, some chemical reaction you have done. What chemical reaction you prepared? What chemical molecule you prepared? You know benzoic acid, very simple molecule, benzoic acid, you know. Benzene, you know. What is the structure? C6H6. It is a regular hexagon, correct? So planar hexagonal structure, you know the structure. But once you prepare the molecule in the laboratory, a new molecule, you don't know the structure. But only after knowing the structure, you have to proceed further, right? So what is the importance of the structure? For example, you know lock and key model of the enzymes. Lock and key model of enzyme. You know the drugs. For example, some cancer drug is prepared. So how it go and act on the system? So there is a receptor in the cancer cell. Okay. The cancer cell having particular structure. Okay. So on the structure, your drug has to go and sit. If you know the structure of the receptor, whatever the cancer cell receptor, then only you can be prepared. You are going to prepare a suitable drug that exactly goes and fits into the cancer receptor, so that the cell division stops. So if you are preparing a different structure, so it won't go and bind into the receptor, so still the cell growth continues. The mitosis continues, cell growth. So you know the tumors, big tumors. So one cell divided into 2, 3, 4, 6, like that. So it keep on continues until a proper drug has to come and fit. So to know that, you should know the structure of the receptor. Exactly you have to make the molecule, and that structure you should know, and both has to go and bind. And once it binds, the inside chemistry works, and there is a ATP release and some kinetics happens over there, and then the cell growth stops. So everything to happen, you should know the structure first. Okay. To identify the structure, whatever the methods we use, that we call it as spectroscopic methods. Okay. Right. So this is the theme of this year's theme. Empowering Indian youth for global leadership in science and innovation for Vikasit Bharat. You should know what is empowering youth. So you should have to gain the knowledge of basic sciences first. Basic science is always the topmost science. So though you will become later engineer or medical, whatever the officer or your profession will be, the basic science only helps you to go into that stage. Okay. So I'll directly go into the applications of the spectroscopy. Everybody knows this. Sir just now show electromagnetic radiation. Okay. So there is a different wavelength of electromagnetic radiation, and different wavelength of electromagnetic radiation supports different spectroscopic analysis. Okay. You know gamma rays, it will kill cancer cells. X-ray, what is the role of X-ray? You will get to know the bone structure, correct? There is some fracture, you go to the hospital, take the X-ray. You will get to know the breakage, correct? Microwave, you can use the microwave for cooking purpose. UV, the UV rays, you can use some protective shield for the harmful thing. Okay, next, what is IR radiations? You know IR radiation, night visible cameras, you know. The police, military officer, they put the cameras in the streets. So they will detect the movement of any organism even at the night visible cameras. And this particular remote, so this is operating on the principal infrared radiation. So these are the general applications. So what is UV? You know radio waves? Radio waves are responsible for the satellite communication, correct? So these are the general applications of electromagnetic radiation. When it comes to spectroscopy, we need to learn deep into the electromagnetic radiation in order to know the structure identification. So what the whole story tells you, for example, here I have written some of the methods. What is NMR? BSc students, what is NMR? Nuclear magnetic resonance, correct. ESR, electron spin resonance, mass, UV visible, microwave, X-ray. There are different spectroscopic methods, okay. So I will directly tell the application of radio waves. So radio waves, we know that radio signaling, so signal purpose, satellite signals and all. But in physics and chemistry, we use the radio waves for the structure identification. How? You see the instrument, we can call it the NMR instrument, nuclear magnetic resonance spectrophotometer. You know the cost of that? It is not less than 4 crores. A minimum basic instrument costs nearly 3 crore rupees. Okay, what is its role? So it supports radio waves. If you have prepared some molecule, for example, some organic molecule, you know benzene, you already know the structure of benzene. Imagine you don't know the structure of benzene. You prepared some new molecule. Once you put the new molecule into that instrument, that will give the signals, a simple signals, lines. Okay, based on the line intensity, line position, you will get to know how many carbons are there, how many hydrogens are there, whether hydrogens are equal or unequal, carbons are equal, unequal. Thereby you will get to know the structure, carbon and hydrogen structure in the molecule. Very simple. Okay, and similarly, see, this is a chart for carbon as well as proton. So in this NMR, nuclear magnetic spectrophotometer, which we use radio waves. Okay, so in general, radio waves helps you to get the signaling purposes, radio waves, radio signaling and all communication purpose. But what we use here, some parts per million, some scale. So 1 to 12, 14 and here 0 to 220. So if there is one signal comes at this position, for example 1, we will say it is alkane. If a signal comes at around 7, you can say it is aromatic compound. If you will get a signal around 14, there is a carboxylic acid. Okay, like that you will get to know the environment of your carbon skeleton. See the application. So what happens in general here, you know atom, electrons, neutrons, everything. So once the electrons you put in between two radio magnets. So if you put an electron in between the two radio magnets, there are plenty of electrons in the outermost shell. All the electrons align into a single position. It will be randomly aligned earlier. So once you bring those electrons into the in between the radio magnets, all the electrons, whatever the random positions, it will align to one direction. Okay. So there are different set of hydrogens in the molecule. There are different carbon sets. For example, carbonyl, C double bond O is a different carbon. Okay. Here R is H, CH, and one more is aldehyde. So different carbon environment, different hydrogen environments, different sets of electrons are present. So different electrons align when it comes in contact with the radio magnets. So thereby you will get to know, based on the alignment of the electron towards the radio wave, you can identify whether it is alkane, alkene, aldehyde, ketone, aromatic ring, all such things. So it is a simple energy supply to the electrons so that it will come into one position. Very basic I am telling, okay. And next, microwaves. So you know the microwaves which will be used for multiple applications. Even chemistry also we will use microwaves. This is what is this? Microwave oven, cooking purpose, right? And this is a microwave synthesizer. So generally a chemical reaction, if you put in a round bottom flask and heat it for 2 hours, 10 hours like that, right? So the same chemical reaction, if you put in this microwave synthesizer, it will be done in 1 or 2 minutes. So very fast energy supply takes place. So this costs around 25 lakh rupees, very small instrument. But application is more. And this is an infrared spectrophotometer. You can see the infrared spectrophotometer. It is hardly a small 2-feet machine, and you are going to put a sample over here and you will pass the IR radiation from the instrument from here. Okay, hardly 1 milligram of sample is enough. Okay, here you are putting a infrared radiation. So in the earlier case, radio waves, and here infrared radiations. If you pass the infrared radiations into the sample, the electrons, so they absorb the energy, and thereby there will be bonds. C double bond, C single bond, C single bond, correct? You know water, H2O. So 2 hydrogens to link to 1 oxygen. So the movement of the molecule takes place. So for example, there is a water molecule. O, H and H, they connected. So once you pass a infrared radiation to this, so the molecule bends. So it will bend like this. So it will stretch and it relax. So it will shape up the molecule based on this stretching and bending vibrations in accordance with the IR radiations. You will get to know what kind of functional groups present. You know carboxylic acid. What is the functional group? COOH, aldehyde. CHO, alcohol. OH, amine. Nitro, NO2. Okay, if a molecule contains such functional groups, so if you put into the infrared spectrophotometer, you will get to know whether OH is present, CO is present, COOH is present, aldehyde is present, amine is present. All those things you will get to know by putting the sample into the infrared radiations. Okay, see now this is a picture of IR spectra. Once you put a sample into the machine, you will get a picture like this. So now you can see the signal over here. So this is 1736. So if you get a signal at 1700 approximately, it is an indication of presence of C double bond O. Okay, if you have a broad peak here, so here CH stretching and CH stretching, and there is some stretching OH. If there is a bigger compound, there is a NH. So based on the different positions of the signal, you will get to know what kind of functional group is present. Okay, this is the second one. The other one is ultraviolet radiation, UV, visible. Visible light is the naked eye, we can see it. And ultraviolet radiations, the electrons have sigma bonds, the molecules have sigma bonds, pi bonds. You know sigma bond, pi bond, etc., right? So the bond transition happens, electron transition from ground level to the higher energy state, it will jump. Whatever the electrons are present, it will go from the lower energy to the higher energy when you put the molecule into the UV radiation. So what this tells, whether you know carbon-carbon double bond, carbon-carbon single bonds, aromatic rings. So aromatic ring, there are 3 double bonds, right, in a benzene. So 3 single bonds, alternately 3 double bonds. We can call it the conjugation. Conjugation means single bond, double bond like that. Okay. So by putting the molecule into this UV spectrophotometer, what is the conjugation present? So whether it is a blue shift or red shift, okay, that you will get to know. So this is a signal. So very simple signal at 400 and 550 nanometers. Lambda max is 450 nanometers. And see there are how many aromatic rings are there. So what is the conjugation? Double bond, double, single like that. This is a complete conjugation. So you have a molecule without any conjugation, you have a molecule with conjugation. If you put both, you will get one signal here, one more signal without conjugation around 200. So there is a difference. Okay, so this is simple UV and this is the X-ray. What I said already, for X-ray, you can detect the bone fractures. We know already that. So now what is the application of this particular X-ray? You know the sugar crystal. Sugar, you know, right? It's a crystalline, highly crystalline. You know the structure of sugar. What is it made up of? Sugar. What is the basic unit? Glucose and galactose. Correct? Huh? Sucrose. Correct. Okay. So you don't know the structure. You know it's a 6-membered ring. 2 6-membered rings in between one hydrogen and another 6-membered ring. Both are connected by 1,1,4 bridge. Correct. This is what the structure. But to get to know the structure, very simple. Place the crystal inside this instrument. If you put a single crystal inside the instrument, that instrument tells you the complete picture of your molecule. See the structure. So you need not to go with 1H NMR, 13C NMR, microwave, UV, nothing, not required. If your compound is crystalline, you will get the structure of a molecule. With the structure, what is the bond distance, what is the CH bond distance, how many double bonds are there, what is the molecular formula, everything comes in one single shot. So that is, we can call it as a single crystal X-ray diffractor. But sir just now told about nanomaterials. Okay, majority of the nanomaterials are not crystalline. Only few molecules are crystalline. Other molecules are powder. In nature, we cannot make all the molecules crystalline. So some may be crystalline, some may be powder, some may be volatile, some may be gaseous, some may be liquid. If the powder is there, then what to do? Get to know the structure. So there is another method, we can call it the PXRD, powder X-ray diffractometer. In the powder X-ray diffractometer, you will get a signal like this. Okay. So you have to put some more supporting data along with the powder X-ray, then you will get to know the structure. Okay. Next. So gamma radiations also have a important application in the field of medicine. It can be used for killing the microorganisms or cells. Okay. So another application, you know, optical microscope, TEM, transition electron microscope, and scanning electron microscope. So scanning electron microscope and TEM is used for identification of the structure of the molecule. Nanomaterials are prepared, right? Sir told you how to prepare. So once it is prepared, how to know the measurement, whether it is nano, micro, all those things. So you have to see the molecule in a spectrometer. Okay, you know optical microscope, all biology students, you know microscope, right? Regular microscope. You can see the structure, right? And the material is very nano, very small. It is not possible to see even under microscope. In such case, what to do? So you have to put the material or molecule inside this SEM, scanning electron microscope. So if you put a small material under that, and here what is the energy here? So you have to bombard the electrons. From the top of the machine, you have to pass the electrons. So electrons touches the material and it will disperse into scatters. Okay, some will be scattered, some will be absorbed, some will be transmitted, all those things happens. So every electron's movement will be captured. Okay, once it is captured and sent to the computer, it will tell you the structure, outermost structure of the material. Okay. So this is a SEM instrument and you have to pass the electron using an electron gun. So there are some cathodes, anodes, some magnetic condenser lenses, everything. So this is a material where you place your sample and these are the detectors. So whatever the electrons comes and hits here, they will scatter. We have to measure it by capturing it. So different energies they scatter. So you will pass 1 kilometer speed. So once they scatter, it may be increased or decreased. So all the electrons, however they scatters, you have to capture it. So once you capture and do the analysis in the mathematical model in the computer, you will get to know the surface structure, outermost structure. So if you put this material and pass, you will get to know the structure inside, structure whatever it is. But when it comes to TEM, so same mechanism, but what is the application? What is inside this? That information you will get to know. So the electron goes inside and interacts with the matter inside, and whatever the internal things are there in this material, you will get to know the information. Very simple. Okay, and now you can see the pictures. These are the cells, different COVID virus cells. So we'll get to know all these structures based on the technology, SEM, TEM, microscope, all those things. Okay. So these are the pictures of molecules which can be recorded through the single crystal XRD. Okay. So if you want to learn all these things, you have to go into the next level education. Don't stop your studies after BSc. So there is more scope for post-graduation and research students. So once you enhance your skills and knowledge in different areas of this, you have a very bright future. Whatever you learned so far here, it is only basics. Okay. So if you want to pursue higher education, be fit in the society, so you have to do some higher education, definitely you have a very good scope. Okay. In this next 5 minutes time, I will close. So what after BSc and MSc? So many are willing to go for higher education. How many? Can you raise your hands? After BSc, stop, huh? Huh? No. You should not do that. So that is what the theme. So empowering youth for science and technology. So that means you have a more power to run the nation. So you should not stop your career after BSc. You can stop. But where you will be once you stop? You may be like other your parents or your grandparents and all, the same way. But society is now focusing on technology and all. And you people have to do that. What are the next? You can do MSc, master's program. Okay, so first thing, what we focus after BSc and MSc, job. Correct? Everybody looking for job. Some people go to the higher education for PhD purpose, higher education. After that, job. Correct? That is the only thing. First job, rest next everything. So we have to feed ourselves and we have to take care of the others. So what job you are going to fit, that is important. You have to earn your own job rather than you have to work with someone. Okay. So once you want to get a job or higher education, there are plenty of opportunities. So you have to write the examination, bank examination, civil examination. After BSc, you can get the jobs. Okay. And for higher education, now it's a competitive world. So you have to write some entrance examination, even to enter into the master's program, right? So you have to write some entrance examination. Entrance examinations will be conducted by the university or some other private sector. So you have to clear the entrance examination, get the rank, get into the subject. Okay. Next one. So there are some institutes, they offer very nice master's program along with, we can call it as a. So those who wish to pursue higher education like PhD, research, etc., you need not to join MSc college, a college with only MSc. You can directly opt for a integrated program. So in the first year itself, you are going to learn all the methods whatever I spoken, and it is a research orientated. From first year MSc itself, you are going for a research. So that by the end of your 5 years program, that is 2 years MSc and 3 years PhD, basics, everything you might have learned in the first 2 years, and 3 years will be your research. So you are going to work more with research fundamentals in the basics itself. So this is a nicer National Institute of Science Education Research, and there is another IISER, Indian Institute of Science Education Research, IITs, CSIR laboratories. So there are plenty of laboratories in India. They offer different courses. Okay. So another Tata Institute of Fundamental Research. So here you can see students are admitted to TIFR through rigorous selection process, which involves written test followed by interview. Selection is strictly merit based, and the only top 1.5% applications selected. So if 100 applications goes, only 1.5 application will be selected. So if 3 candidates get selected, means they are from the 200 applications. So that much strict rigorous selection procedure will be there. For that, what you have to do? From BSc itself, you start learning. So you have to learn for competition exams. Okay, not just learning for examination, scoring the marks here. If you are looking for higher position, you have to start now. Okay, and PhD after master. So if you want to do PhD after master, there is a CSIR examination. Once you qualify CSIR examination, you will get around 38,000 per month as a fellowship after MSc. So after MSc, clear the exam, join into some organization for PhD. From first month itself, you will get now 38,000. If 8th pay is implemented, it will go around 45,000 rupees. For 2 years, you will get 38,000 rupees, and next 3 years, you will get around 48,000 rupees. If 8th pay is implemented, it go up to 50,000 rupees. Okay, that much salary even you won't get once you go for a job after MSc or BSc. Okay, so this supports your regular things as well as you will get the degree also. Okay, so in Karnataka also there are 2 CSIR laboratories. Each and every state is having CSIR laboratories. I will share all this information. And joint entrance examination you have to clear to crack many of the entrance jobs and all. And 23 IITs are there in India, and JEE advanced examination you need to write. IIT JAM you have to clear, or GATE you have to clear in order to enter into the IIT. Okay. MTech after BSc. BSc students have an option to join MTech program. Okay. Engineering program, even the BSc students have an option. So you have to clear JEE exam. Okay. So you have to clear the JEE and GATE examinations, and you should have minimum of 50 to 60% CGPA, basic level. Okay. I will share all this information. So we are from Reva University. Our university also offers many of the master's program. UG and PG programs. Majority of you people may already came to our campus and you have done the project internships and all. So those who are interested for master's program in any of the specialization, I think the brochures are given. So you can look into that. And we have a very nice opportunity for research. And from the day one, we put the student for research. Okay. So it's a though master's program, we involve the students in the research from day one. So you look into all those things in the brochures. And we have chemistry around 60 openings, and biotechnology, maths, all the programs we offer. So please, you refer, and if you are comfortable, you can come and visit our campus. So with this short presentation, I'll stop. Thank you so much.
To speak few words about the talk. Few words.
A very good afternoon to all, the respected dignitaries and the resource persons of today's event, Science Day. Dr. Shivanna sir, and Dr. Nagendra sir. So I thank from my bottom of heart, because of that means today's event, they have come all on the way from that was Bangalore, and has been spent a maximum time to give you the good ideas and knowledge regarding the science. Science people already always disciplined students and very good students. And moreover, these type of activities will be done more and more number in science department. So we are very happy to be a part of this event. And I know words to express, because I think actually maximum you have been utilized whatever the resource persons has been given the information. Once again, all the best students for this Science Day program. And once again, thank you for giving this wonderful opportunity. So thank you.
Thank you, ma'am, for giving the awareness about the scientific things to the students. Now I would like to call our secretary, Madam Srimati Usha Gangadhar ma'am, on the stage to address the gathering.
Good afternoon, students. Dignitaries on the dais, respected teachers, and science students. I'm very happy to see the science students, as I'm also a science student, that's what. Yeah, your HOD told me that, Madam, you have more confidence on science students. Yes, sir, I am right. You are right. So I have more confidence on the students. No need to watch them also. They'll hear the today's resource persons talk and all. They'll learn and they'll go ahead for the implement in their life and all. So when I heard about today's resource person's profile and all, I'm really surprised and so happy to see you, sir. Such a good and big profile they have. We are very small in front of them, and so I'm very happy. So my dream, one of our students has to become like that only. So one day we'll call you as a resource person. That is my dream. Just let my dream come true, no? Okay. So we have to thank your HOD to conducting such type of programs for you, especially for the science students. Really, it's good. It helps in your studies and all. Go for a research work and all, higher studies. So I wish all a happy National Science Day for you. For me also, I'm very happy to celebrate this Science Day. Thank you to call me again. So it helps you a lot, I think. So once again, I'll request a HOD to conduct such type of in other subjects also, not only in chemistry, physics and maths is also there. So that instigation will take in the coming days and all. So physics and maths, computer science also. So we'll do the best. So once again, thank you, resource person, thank you students, thank you all the science teachers.
Thank you, ma'am. Thank you, ma'am, for your encouraging scientific and inquiry students, and they have gained valuable and perspective from the youth talks. Thank you, ma'am. Now I will request Patil sir to deliver a few words regarding. Okay. Thank you, sir. Please, sir.
So good afternoon. Okay. As madam said, I am also very proud to say that I am also science. Okay. I have done MSc in physics and PhD from Karnataka University, and my topic is also related to a chemistry. Photophysical properties of some organic compounds, where I used a spectroscopic technique only to analyze. So happy to see that spectroscopic techniques today's topic, and of course nanomaterials I have not used. And also my specialization in MSc is spectroscopy only. So continued with the same. Thank you for giving me opportunity to talk to you. I don't want to take much time. I wish you all the best. And science is always the best. Okay, and you have chosen the best course and have a great career. And thanks to Hari Krishna sir, he is very innovative. Always thinks about students only, and the activities for the students. So not just book knowledge. So more and more exposures he will give. So thank you Hari Krishna sir for such a good initiative. I think we will try to push as many as our PU students, science students to BSc. Okay. Thank you. Thank you. Thank you, sir.
Thank you, sir, for sharing your experience and some inspirative thoughts about science with our students. Now I request our dignitaries to facilitate our esteemed guests, Dr. Shivanna M. sir and Dr. Nagendra G. sir. our honorable guest, Dr. Shivanna M. Sir and Dr. Nagendra Sir, for sharing their valuable time with us. Now, I thank you all for making your part of this prestigious event. To present vote of thanks, I would like to call Professor Sujata Ma'am for the stage.
Good afternoon, all. It's a great honor and privilege to propose vote of thanks on this memorable occasion. First and foremost, on behalf of SDC Group of Institutions, I would like to express my heartfelt gratitude to our esteemed chief guests, Dr. Nagendra Ji and Dr. Shivanna M, for gracing this occasion with their presence and giving a wonderful on nanomaterials and spectroscopic techniques. Thank you, sir. I extend my sincere gratitude to the Secretary of SDC Group of Institutions, Srimati Usha Gangadhara, for her invaluable contribution to today's National Science Day celebration and for her continued dedication to fostering scientific advancement. Thank you, ma'am. I deeply thank for the leadership and support provided by our esteemed principal, Professor K. Pushpalata, in executing today's event. Thank you, ma'am. My sincere thanks to Vice Principal Professor Satyajit Ray in making today's celebration a resounding success. Also, I like to thank Dr. Shivram N. Patil, sir, for being a part of this event. Thank you, sir. I would also like to express my heartfelt thanks to the organizer, Professor Hari Krishna, HOD, Department of Chemistry, and all the HODs of various departments and teaching faculties for their tireless efforts in making this event a memorable one. Thank you, sir. A special thanks to PRO Mr. Arun Prasad and technical team for constant support in making the event successful. Thank you. Finally, I would like to thank all of you for being here today and making National Science Day celebration a grand success. Thank you all.